afternoon to you all. Well, my name is Arvind Keprate, and I work as a senior engineer with DNV. And in these 2 days, what I feel, we have been hearing a lot about sensors and data. But my question to you is, what happens if you can't place a sensor? For instance, how do you place a sensor on a 500 kilometers of a pipeline? And if you don't place a sensor, you don't have any data. And you don't have expert judgment. How do you go ahead? First is that. And the second thing, what we have been hearing a lot is about that people have been talking about the downtime maintenance, and they have been talking a lot of the cost savings. That is what predictive or prescriptive maintenance means for them. But in the oil and gas industry, there is another thing which is more important to us, and that is the safety and the environmental aspects of that. So when we talk of the pipelines, definitely we have to save a lot of bucks, but we also have to think about the safety of the people, of the environment. And that is what is of paramount importance. So that is why what I will be talking of is not a digital twin, but a probabilistic digital twin. That is, it is a marriage between a digital twin, with a dynamic risk models. So that is what a probabilistic digital twin is. So a little about my professional introduction. So you can see, but the main focus, what I wanted to point here is that while I was researching, I had a chance to be at the NASA Ames Research Center at the Prognostic Center of Excellence. And it was there where I was introduced to this concept of machine learning, artificial intelligence, predictive maintenance, prognostics. And after that, I have been serving DNV as a senior engineer. And the fun fact is that about 5 years ago, when I was about to get married, so my wife asked me, so what do you do in Norway? And I told her that I'm a pipeline engineer. And then what she thought was that I was a plumber. And then I thought, this incident came up to my mind, and that is why I thought that people don't have, when I say that I'm a pipeline engineer and when I say of oil and gas people, I mean common people don't know what this is. So I need to explain a bit about that. So I will be telling you a little about the background of pipelines and the sector where I belong from. So what is DNV? DNV is a corporation, I would say, and which is having its roots about 150 years ago, and they started with the maritime business. So yeah, I hope if someone of you have been to the Royal Caribbean or the Color Line, these cruises, so they are actually verified and certified by DNV, but that is their maritime business. And another funny fact is that while we were getting this training, when we were inducted into DNV, so one of the guys asked that, what about Titanic? Did you guys certify that? And definitely we didn't do that. That is what we have been told, because we know the history of Titanic. But I belong from the oil and gas sector, and in oil and gas sector, I belong from the pipeline sections. And I'm really proud to be part of that. And the reason is that 65% of the offshore pipelines, and I'll explain you what offshore pipeline is, they are actually designed, operated, and maintained by our standards, which are free of charge, definitely. And now, let me go back to what from the past 2 days we have been hearing, digital twin. So one of the, I would say, the famous guys in this field, he said that if we are to compare oil, then we would compare it to data. And if we have to compare the ICs or the internal combustion engines, we would compare that to analytics, okay? And then we hear a lot of buzzwords, IoT, that is what we have been doing right now as well. IoT, artificial intelligence, machine learning, and all that stuff, right? And twins, we already know what twins are. We already know the lessons like a Siamese twin, something which is very similar looking. But let me give you a perspective from a mechanical engineer, how I perceive what a digital twin is. I consider this, that there is some physical asset, and then you try to replicate the physical appearance of that, first of all, into the virtual space. And then, and then you get what you call as a twin, right? And a digital twin. And then another important aspect is that there has to be a digital thread. What is a digital thread? You have sensors on a physical asset, and you have some sort of way of capturing that information from a physical asset to your virtual environment, and that is what a digital thread is. And then whatever forces or loads you apply on the physical asset, they should be exactly simulated on the virtual asset so that you can simulate. So that is one way. And now what we have to think of is I mean, one of the best examples which somebody gave to me of the digital twin, which we can easily relate to, is of Tesla, right? I don't own a Tesla, but what one of the guys who have been using it, he says that what is the different approach of Tesla, what the others don't have? That the different approach is that they are a software company and they are building cars. However, Volkswagen is a car company and they are now going into the software business. So there is a huge difference. And one of the examples, what a digital twin of Tesla does is actually, for instance, if you have a rattle in your, I'll say the door, so what they do is they just update software in US and the rattle will be finished. So it's not like Ford recently called about 3,000 vehicles back to their assembly line. So that is what is the power of the digital twins. And here the example which I'm giving you as one of the guys in the recent presentations, he presented how do they actually predict when their batteries will fail. So that is for the electric vehicles, that is something which is very important. So here in this pictorial representation, you see the idea of what a digital twin is. And over the ages, so the concept of digital twin is not new. It was actually in 2002 when this term was coined. And ever since then, there has been a great evolution. So I would like, if you see this graph or the picture over here, you can see the past. So I would like to say that this part, what we say as the status only. And if we go back to what we have learned from the past, in the past 2 days, this is something which is very similar to what we call as our condition-based monitoring. So here you get the status of what is happening, right? And then what is the present? The present is that you have operational and the simulation twins. And that is where we are heading now. That is the predictive and the prescriptive. And then the final one, the future, what everyone is talking of is the cognitive. That do the computers have that ability to give you what you want? So that is the future. Okay, so now enough of the digital twins, and now let me ask you, what is a pipe? So I didn't want any of you to have the same frame of mind which my wife had 5 years ago. So I thought, okay, let me go to Google and let me ask this question, what is a pipe? And go to the images. So what do I get? I get this image. I mean, this is not certainly what I'm looking for, right? Then I again try to find what is a pipe, then a lot of plumbing solutions come in. I mean, I almost spent 2 hours to get one image of pipeline, which is very kind of famous in my industry, but which I would like to have it so most of the people understand. So this is generally a sort of a pipeline which we say in oil and gas. So what you see here is, this is a steel structure, and over here you have the concrete structure. And this is a 24-inch pipeline. So just to give you an example of what are the pressures which are in an oil and gas pipeline, so if you see a 16-inch pipeline, and if you compare it to Boeing 747, so you can see the comparisons. So the operating empty weight of a Boeing 747 and a 16-inch pipeline, which is having a 200 bar, they are almost equal. And then we have 2 different categorization of pipelines. If it is running on your land, it's called as an onshore pipe. That is something which you will most commonly find in Dubai or Americas or Canada. And something which is under the sea, as you can see a lot of corals and fishes around. So this is what we call as an offshore pipeline. And then last but not the least, this is what a subsea production system looks like. So this is, you have a ship, you have all the facilities over here. Here what you see, these are called as risers. They are vertical. And then these are what are called as the infield pipelines. And what I am interested today is in this, the red one, the gas export pipeline. That is a pipeline which will take all of the oil and gas from here to a terminal and then from the different distribution systems. And since I'm talking of the export pipelines, so this is how the map looks like for the Norwegian continental shelf. And this is actually, let me emphasize once again that this is, all of this is under the sea, on the seabed. And what are the facts? Some of the facts are that this, what we see here, Norway, in the Norwegian continental shelf, they have the longest network of the pipelines. And then Norpipe, that is, this was the first one which was installed in 1977. And just to give you an idea, if we want to transport gas from Norne, that is somewhere here, to Dornum in Germany, it takes almost 5 days. That is, the gas will travel from here to here in 5 days. And these are the gas pipelines. So the total accumulated length is around 8,000 kilometers. And again, it is because of these pipelines that Norway is catering for about 25% of the energy consumption of the EU. And finally, if the production stops, we are talking of about $60 million of losses per day. So my emphasis is of this whole network and these facts is that pipeline is an important asset, not only for the world, but especially for Norway. It is a very important asset, and we need to maintain its integrity. And there, just like any other equipment, there are always two questions. Either if you save too much of money, then you are increasing the risk. So the choice is always between whether you want to save money and increase the risk, or you want to reduce your risk, increase safety, and finally, you are ready to spend some money. So how is the integrity of the pipelines maintained? How do we do that? So let me, how do we do that is, it is with the help of a pig. And when I call pig, so I mean, I have a 2-year-old daughter. So for her, the pig is Peppa Pig. I mean, now she doesn't resemble my photos, but whenever she sees Daddy Pig, she's always saying Daddy, Daddy. So it's kind of a bit of struggle to me. So what we do is, if you ask someone, they'll say that they will run a pig through a pipeline. So what do we mean? We don't mean something like this, but PIG stands for Pipeline Inspection Gauge. And it looks something like this. So what we have the cleaning discs over here. We have the rollers, we have sensors, we have magnets. And this picture will give you a brief introduction to that. So we have sensors, we use sensors. And the common sense tells us that rather than putting sensors at every kilometer on a pipeline, why don't you run sensors through your 500-kilometer pipeline? So in that way, you capture some data. That makes sense. And when we do that, but then the cost is, and then the question is that you don't have a continuous digital thread. How often should you run a pig in a pipeline? Generally, the operators would say 3 years, 2 years. So you have data, but at an intermittent level. You don't have a continuous digital thread, which is kind of a necessary for a digital twin. And then the second is, as I mentioned, sensor location is a problem. For instance, somehow we say that let's install sensors at an interval of 10 kilometers. But one of the biggest threats to the pipeline industry is corrosion. And corrosion is a local phenomenon and not a global phenomenon. So even if my sensors are giving me reading at, say, this kilometer point, it's not, you can't just predict that the corrosion levels would be same for the next 10 kilometer point. So that is why we run a pig. And then the third is, the cost of running this intelligent pig is about $1 million. So how often do we run it? If we run it every 6 months, then it means that who is going to pay that digital bill? So it's always cost, that is money, and the safety, that is we are worried about. So we are in this conundrum. We want to, how do we use a digital twin into something like a metal with a hole? That is what a pipe is. And then we were challenged. And this is what I will be talking of. That is a pilot program, actually. We haven't, we are trying to sell it to our customers, but we have developed it by ourselves. And that is where probabilistic digital twins come into place. So digital twins, we all are aware of. And then are the risk models. So what are the dynamic risk models? They are actually allowing us to capture uncertainty. Digital twins have a lot of information, but they don't capture that uncertainty. So how do you do that? That is just a confluence of these two, and you get probabilistic digital twins. So again, to put it in a different way, this is what we know. And this is what we built a layer on the top of that. So what are the components of probabilistic digital twins? You have the failure and the degradation models. So one of the examples of that is structural reliability analysis, and I will be talking of that. And then second, and the most important part, which I think is logical and relational models. And these models, one of the examples are probabilistic graphical models. So what are probabilistic graphical models? So these are two examples of that. One is the Bayesian network and the Markov network. So X, Y, and Z, what you see in them, these are called as the nodes. And this is where you put in your random variables. So you start with this phenomena that you know something, but it's uncertain. It's not unknown. You know something, but it's uncertain. And what are these arrows or these arcs? These are the probabilistic relations between them. And on the top of that, if you would like now this is something we are talking of the cognitive thing. You can even have the decision context on that. But this is something which is in the future, I would say. And now let me give you an example and discuss the components of PDT. So first, as I said, was the the structural reliability analysis. So what is the structural reliability analysis? For this, consider that you go into a gymnasium, right? And then you see a heavy weightlifter, he's doing a bench press of 200 kilograms. Now, would you do the same thing? No, you wouldn't do that. And why you wouldn't do that? Because you know what is load and what is your capacity to lift the load. So that is all what we are doing in structural reliability analysis. We are just trying to see that you have a pipeline, what kind of loads it will be subjected to, and once you know, you see what is its capacity and you compare them. But now the question is the loads. We are not dealing with the deterministic loads here. We are dealing with the probabilistic loads here, which means that you have to try a combination of loads. Even if the quantity is same, you have to have some sort of uncertainties on that. As you can see in this pictorial presentation, a 50 kgs, maybe the guy lifts this, but maybe in that scenario, he fails. So you have to try different sort of combination of loads. And if you present it in a bit engineering way, so this is how a structural reliability analysis looks like. So over here you see, here we have data. This is the historical data, right? And now this, as yesterday one of the speakers from Urista, he said, so this can be one data coming from your sea waves, one from the wind. So all of the loads, we have some data and we try to fit a distribution to that. And then on the top of that, we have certain uncertainties associated with that. And then we have the structural model. So what is the structural model? This can be actually your finite element model. And this is where the role of digital twin comes in. So you have this digital twin, and then you have a capacity model. So what this function, the limit state function, which is also known as a failure function in other domains, you are just trying to see and if your capacity is higher than your loads, and if it is higher, then you are safe. So you are calculating that safety margin. And so this is how you would see your probability distributions would look like. So what is of point of interest is that this is your failure area, where your load effect is actually larger than your resistance. And so finite element model, that is the digital twin, would give you the load effect, and the capacity model would give you the structural resistance. But now these digital twin or finite element model which we use, we know that they are computationally expensive and time consuming. If you want to build a high fidelity model which would capture the exact phenomenon or the physical phenomenon, what your physical asset is going through, it can be very time consuming. So that is why what we try to do is, we try to use surrogate models. So what are surrogate models? So these are the models actually, what we try to do is we build a finite element model and then we use that finite element model to get a data set, say 100 data points. And then this finite element model is actually capturing your input and output parameter space. And once you have this training and test data set, you have your surrogate models, or in simple terms, your machine learning algorithms, which could be a Gaussian process, KNN, or even a simple linear regression would suffice. So you just try to train and test it, and hence you build a response surface. So now you have input and output parameter space, and now rather than using your computationally expensive finite element model, you are using a surrogate model. And if you present, so this is how the flowchart of it looks like. And this example would actually give you the essence of what I'm saying. So over here you see the first thing, you build a digital twin. And then this is slow, which means computationally expensive. Then you are using this one to create a data set. This data set is in turn used to train and test a model. And this, let me tell you that this whole process, this is an iterative process. So once, with the help of, as you know, with the help of Gaussian processes, what you can do is you can even predict the uncertainty in your prediction. So that is why Gaussian processes are very important. And once you have got the response surface, you just use them. You just replace your FEM, and you just use this FEM for further calibrations. You don't use it. And in that way, you can actually save a lot of time. So all the process of using surrogate models, that is just to save time, and definitely not to compromise the accuracy. And the second part, that is the logical reasoning. Yesterday, Professor Dimitri presented that we have to capture that field. So what I think that Bayesian networks are also capturing the logic which the human experts have. It's not, so machine learning will capture those things, or the data-driven aspects capture those things. They don't, I feel they don't capture the field. But over here, what you see, Bayesian networks do that. So let me emphasize what a Bayesian thinking is. Bayesian thinking, it is a very simple phenomenon in which we make our decisions day to day. You have some prior belief, and then you do a test or an experiment, and then you have a posterior belief. For instance, let's start with this. Before I moved to Norway, I never liked coffee. I mean, it's strange. You are in Europe and you don't like coffee, right? But then few of my colleagues told me, okay, why don't you try it? I mean, by coffee, I mean the black coffee, not like the cappuccino and the American type. And then I tried it once, and then I started to like it. So my prior belief, which was not liking coffee, changed to liking coffee. Why? Because I tested an experiment. I tasted the coffee, right? So this is a simple way. So the same thing is shown in this pictorial representation. So you do certain tests and experiments. You get new information, and then you get the posterior probabilities. And that is what the Bayesian thinking is. And we do it in day-to-day things. For instance, you see, after this talk is finished, at 3:30 you want to go out. And in the morning you saw that, okay, the weather forecast is good. You don't need to carry umbrella. So your prior thinking is, I'll go without umbrella outside. But the moment you step outside of the hotel, you see, okay, it's drizzling. So then you carry an umbrella. So what has happened? You got some evidence. You changed your beliefs. And then, again, a simple story. So let's see. He's Jan, and he's NA. So Jan wants to propose NA, right? So what he does is, before proposing, but NA is also very clever, what she does is, NA wants to test whether I want to say yes or no to the marriage proposal. She wants to test Jan. And Jan is an engineer like us who believes in Bayesian thinking. So the prior belief of NA was that I will marry him. And Jan says, now Jan asks the question, will you marry me? But the test is, she says that, will you love me unconditionally? But what the guy says, sorry, I can't, I have Bayesian thinking. I mean, he was being too practical. But then, what is the posterior? This is the posterior belief. So through this, this comic way of presentation, I want to make sure that people understand what Bayesian thinking is. It's a very simple phenomenon, at least to explain. But yeah, when we deal with probabilities, it's a very difficult thing, I must admit that. So now what are Bayesian networks? So it is a simple way of representing the Bayesian thinking with the help of directed acyclic graphs, which we call as DAGs. So directed, I will tell you why they are directed. Acyclic, because there are no cycles in it, like in the Markov networks. So now let's play a simple game. So here, so this game is actually, if I tell you something about, you can even read through it, but it is something like this, that given I tell you certain features of an animal, would you be able to guess what animal you have in your mind? So this is how the Bayesian network looks like. So first of all, two important points. The first is, these are the nodes. So the topmost one, that is the parent node, and these are the child nodes. So this is actually a child node of this parent, and this is actually a child node of this. So this is very intuitive. Parent comes on the top, hierarchy follows. And the second is this. What is this? So these arrows, this is called as directed. That is why we call them directed, that they are directed from parent to child always. And then these actually, arrows, they have the probability dependencies between them. And how do we fill that? One way of doing that is conditional probability tables. But that is not the only way. Now the Bayesian networks have reached to such a level that we can even train them with the help of various machine learning algorithms and various surrogate models. And that is what we have done. But this is a simple way how an expert judgment can go in. So now getting back to the game, so okay, this is what we know. Initially we start with the uniform distribution. Okay, it can be a monkey, penguin, platypus, robin, or a turtle. And these are the various factors on which we want to classify it. So now you get an evidence in this game. So the first evidence is that you say that, okay, 100% you know that it is this animal is in water. He lives in water. So what happens? So now you can see that, so the uniform distribution changes to this. So you are definitely sure that it is not a monkey or a robin. So you know that, okay, it can be any of these. And you can also see that how these probabilities are changing. I mean, this is just a very simple example, but the credit card fraud detection and even especially in the health diagnostics, Bayesian networks are very helpful. And then the second evidence which you get is that, okay, it is a reptile. So how does it change? Now you're 100% sure it's a turtle. But what would happen if it was the evidence or not? It was not a reptile, but it was a mammal. So now you say that it is a penguin. So what I want to emphasize here is that as your evidence is changing, your posterior distributions are changing, and you are actually converging. You start with something uncertain, and as more and more information comes in, you try to narrow down into the alternatives or the final outcome, what you would get. And then why I personally like Bayesian network, the first is the representation. As you can see, with the help of these graphs, the problem is, people understand it much better because our brains are trained in that way. And why I say that? So this is a limit state function for remaining fatigue life for the pipelines. And when we see that, most of the people don't understand what this is and what is the relationship. But if I represent the same thing in Bayesian network, okay, at least people will not fall off to sleep. That I'm sure of. And you also know that, okay, what are the parent nodes, that what are my input parameters on which my remaining fatigue life depends. So that is one way. That is Bayesian networks have a very, they have a feel of, they have this feel where you can present the networks in such a way that people understand the problem in a much better way. And the second is learning. As I mentioned earlier, that you can either train these Bayesian networks with the help of machine learning, or you can have your expert judgment. So it is actually, again, a confluence between both of the domains. And the third is the inference, the most important one. So what do I mean by inference? Inference in simple, prior, evidence, posterior. So how do you reach this posterior? That is inference. And there are two types of inferences. So the first inference is causal. Causal means you go from the parent towards down. That is the top down. So as you can see. And the second is evidential. You go from bottom to up. So now how we can use these Bayesian inference for the pipeline integrity, that I will show you. So this is again the same one. So as I said, causal reasoning. When I say causal reasoning, the question you ask the Bayesian network is that, when will my asset fail? So that is the question you ask. And the evidential reasoning is what caused the failure. So the same Bayesian network can give you two different answers to the two different questions. So that is one beauty of that. And now, yeah, this is an extensive example of this. So when we say that in the pipeline sector, that we want to extend the life of our pipelines. So initially it was designed for say 20 years, and now I want to extend the lifetime. Can you tell me, as our the opening speaker said, that we are too much into prognosis. So the answer of the prognosis, that is life extension, it comes from the causal reasoning. And then the evidential reasoning. Once your asset has failed, now you know that you can't extend its life, but it has failed. But what caused it to fail? So that is an evidential reasoning. And that is also you can do with the Bayesian network. And after this, there's a small case study. I also have a demonstrator if the time permits. So the case study, this is actually about an offshore platform. You have an offshore platform, which you can see here. So if you might recall that from the offshore platform, the gas will go through this export pipeline. But now the question is, you have a compressor over here. And this compressor, there are two inputs to it. One is the power, and the second is the outlet pressure. And the second thing is that this pipeline, it is having some capacity. So what you want to ensure is that the capacity of this and the outlet pressure of this. So the outlet pressure should never exceed the capacity, because if it exceeds, then your pipeline will fail. And to protect that, you have this HIPS, which is the high integrity pressure protection system, which will actually, it is a barrier system, safety barrier system, which will actually come into play when the pressure differential between them, because there is a pressure differential, say 10 bar. Whenever there is a pressure differential of 10 bar, it will come into play, and hence this will never reach the capacity and it will never fail. But now, so this is what we have. So this is the physical system. And after that, what we did was we made a digital twin of it in one of the softwares. So what we are actually trying to see is that given your inputs, and the inputs here are the outlet pressure and the power of the compressor, what is the pipeline pressure? That is what we are after. So when we were using this digital twin, it was actually taking us, for each simulation, it would take us say 5 to 6 minutes. But that was, and we have to try, more than 1,000 iterations. So it was a very cumbersome process. And that is why what we did, we created a Gaussian process. We used Gaussian process and created something this. So here you see on the X and the Y axis, you have the inputs, that is your compressor power and the outlet pressure, and this is the pipeline pressure, which is the output, what you are interested in. And the black dots here, what you see are, these are the actual simulations which you get from your digital twin, and then you fit a response surface to this. So we are after this. So now once you have mapped the input and the output parameter space, the next thing is the logical model. So the logical model is very simple. So if there is blockage, if there is no blockage, it means that there will be no burst. That is, pipeline will never the pipeline will never burst. But if there is a blockage and there is sufficient power to the burst pipeline, is sufficient, you go to this step. And given that your HIPS is working, then it won't fail. But if HIPS is not working, it will fail. So this is just a simple logical model which comes from the expert opinion and the intuition. You have this. And then over here, what you see, so this is the gray band. This is actually what we capture from the finite element modeling of the pipeline. And so this gray band is the pipeline capacity. And what you see here is, so these colors, this blue colors corroborates to this blue color. So now you can see that, okay, if I follow this line, the green line, that is, there is a blockage, but there is not sufficient power. So it shouldn't fail. And that is what is shown over here. So green line, and it is not failing. Why it is not failing? Because this line is below this gray band. So whenever all of these lines are in between or below the gray band, the pipeline will never fail. But this was the entire thing, the modeling part. But where is the Bayesian network in it? So Bayesian network, what Bayesian network does is we create all of this into a Bayesian network. As you can see here, you have different models, pipeline structural reliability model, that is, which would have given you this. So now this logic is going into different Bayesian networks. And then we capture all of this, the data and the logic into this Bayesian network. And this would give you finally the output, whether that is the probability of failure, whether your pipeline fails or not. And now over here, I have a small, okay, not to learning conclusions, but it's a bit tricky. No, the suspense is going. Yeah, but maybe I have a simple solution to that. Yeah. So actually, if you guys are interested, you can you will find a link to this position paper, which the guys in the Research and Innovation Department of DNV have written, and they actually explain all of this. What is a digital twin? What are probabilistic digital twin? And here is so this whole concept is explained here as well. But we also have this burst risk monitor. So what you can do is actually, so as I mentioned that this is just a pilot. So this is your current probability of failure, and this is the target is that it should be below this. So as long as it is below this, we say that it is safe. But what we can do is actually we can forecast and predict. So these are the inputs which we change. And when we can, so for instance, if I go here and I change the set point to, so it is this, and outlet pressure is somewhat this. Then I say forecast. Yeah, so it will give me, one is the forecasted probability of failure, and you can adjust that. What interval are you interested? Do you want forecast for 60 days? You can just adjust it here. And the other, it gives me this graph. So as long as my pipeline, so this is the probability of failures, what you get. And what you are actually interested is in this. So this is the forecast. And then you get the warning signal. So once it is critical, it will actually show me that, yeah, this is a critical. And then over here, you can actually go down and you can actually see exact date where it dropped. So if you go here, so you can actually read through these. So this is, and then for instance, you know that, okay, here, because probably a shutdown was planned. So here the risk is very low. But however, at these point of times, you say that the risk is very high. So it is just a simple tool which these guys have developed at the Research and Innovation. But you guys can definitely, I would recommend you to read this. And also this position paper, AI and Safety, where these guys are talking of that how artificial intelligence is important from the safety perspective. Not, I mean, it doesn't matter if you click on a wrong Netflix film which was recommended to you and then you watch it. It doesn't matter that much. But what happens to a safety critical industry such as aeronautics and the oil and gas? So how artificial intelligence is important for that. So that was my presentation, and the last is the conclusions what I have. So our experience with the probabilistic digital twins is that they are fairly accurate, given you have you know a bit of historical data, not a lot amount of historical data, and your surrogate models are very important. Those are very accurate. That is very important. And then the second is that you can build a model, no worries, but you have to be very careful of this garbage in and garbage out paradigm. That is, if your model is perfect, but your garbage data, you would get a crappy output. Likewise for the garbage model. And to summarize, I would say that digital twins, we know that what they are, and then we have the risk model. So when you join them together, you get probabilistic digital twins, and which actually tries to overcome the disadvantages of both. And my finally, I would just like to say, if it works, is that, does it work? Yeah. Thank you for your attention, and this is the team which I had worked with. So that's it. Thank you.